We're going to continue with time and space stepping schemes, and we're going to consider a really diverse number of ways, both implicit and explicit methods, that you can march yourself forward into the future. In particular, there's a lot of choice and flexibility you have in how you decide how you want to march forward. And eventually what we're going to have to really address is what are the appropriate methods we want to be using, and then we're going to have to dig down on issues of stability. So different schemes that you might consider, often the final choice of a scheme is directly related to the stability, accuracy properties that you want to maintain in your solution technique. So let's take a closer look at time and space stepping schemes. And I want to start off with very simple models here. So let's start off with the easiest PD we could write down, really, which is the one-way wave equation. So it's ut equals cux, and what this admits is a traveling wave with speed c. So we know how to solve this analytically, and the question is, how do we come up with a scheme that would solve this in a numerical method? Okay, so first, let's start off by doing center difference discretization of that space derivative. So all we do here for a derivative is use rise over run formula. Point front minus point behind divided by 2 delta x. This is the first thing we learned in calculus. In fact, what we did with calculus is took the limit of this slope formula, take delta x to 0, and that was the definition of the derivative. And now we're going backwards. We're saying, let's undo that derivative and just give it as a difference formula. Okay, so that sets up to take care of the space derivative. And now what we want to do is take care of the time. So if we look at the time here, we want to now start looking at how do I differentiate in time. I can use several formulas, and what we're going to do here is, again, a slope formula where all we're going to do here is forward difference. So we're going to use a slope formula which involves the current point and the time point in front. So notice here, this is the time point in front, this is the current point, and I've already multiplied through by delta t, but this was just a slope formula which was the point in front minus the current point divided by delta t, and I rearranged it into this formula here. And the reason I arrange it here is I want to start to highlight sort of your stepping scheme of how you get into the future. So the superscripts here denote what time point you're at. The subscripts denote the spatial position. So in space, so we're marching forward one step in time, and I'm evaluating this right-hand side at the current time point, and look how I'm using my neighbors with the derivative. So this is a very simple formula here, and now I'm going to rewrite it one last time simply by taking this delta t over 2 delta x and writing, delta c delta t over delta x as lambda. And it turns out this is an important quantity. This is called the CFL, the Courant-Friedrich-Lewis condition number, and the CFL number is absolutely important for stability properties, and we're going to investigate this in detail in the next lecture, but for right now you see that it's embedded right here in front of this term. So the way this scheme works, which is forward difference in time, center difference in space, is right here. So you're using these 3 points to update solution one line into the future. So what I would do for every single point in the future, I'd go to the next point, use the 3 previous points down here to get to this point, right? Go to the next point, use its neighbors here to get this point, and so forth. So I'd walk across this entire line in time in order for me to take a step forward or produce the next line of solutions in time. So that's the basic idea of this stepping scheme. Okay? Let's solve the same problem again with a different method, different scheme. So in fact, part of what this lecture is going to highlight is there are so many different ways that people have developed for doing this method of lines, for advancing solutions in time. And so I'm going to show you a bunch of them here, and many of these are developed because they have, for certain problems, not all problems, but for certain problems, they have exceptional accuracy and stability properties. So for given a problem that you might have, one of your jobs is to figure out what is the best scheme for the PDE that I'm trying to solve. And there's a very big difference about what you would do with a wave equation versus, for instance, the heat equation in terms of stepping algorithms. So let me just show you, continue to develop this for the one-way wave equation. So let's go back to what we had, one-way wave equation. Again, I simply discretize center difference in space. But now what I'm going to do, I have to take care of this time derivative. I'm going to do center difference right here for the time derivative as well. So center difference, interestingly here, I'm at the current time point m. I'm using a point in the future and a point in the past. So that's the center difference. I use point in front, point behind over 2 delta t, which allows me to write this scheme here. Again, there's the lambda, the CFL condition, or CFL number. And what you're seeing here is the point in the future, in the front, in the future, is equal to what it was at time point behind times the derivative calculation at the current time point. This is called Leapfrog 2-2. The 2 and the 2 dictate that it's second order accurate in time, second order accurate in space. And Leapfrog, because what you're doing is at the current point, you're using the time point in the past to produce the future time point, so you're leapfrogging over the current point that you have. To see this in a picture, let me just show you this. So this is the scheme in a picture. So notice you're at this point, if you're going to produce this point here, you're not using this point here, which would seem natural, this is what we used before, but you're leapfrogging it to produce an estimate of the future derivative. And this is called Leapfrog 2-2. So point in the future is what it was one time point ago plus the CFL number times your neighboring points at the current time. Now, the implications of this scheme is, if I'm going to march it forward, I need 2 lines of solutions to produce the next line. So the nice advantage of the previous scheme is the current line of solutions is all you need to advance forward. This needs 2 lines of solutions to advance forward. Okay? All right. But, again, part of what we do it is because we might have nice stability properties, which will show that Leapfrog, in fact, is very good for solving wave equations with wave behavior. Let's come back here, same equation, but now we can do something else. We can improve our accuracy. So if you want to prove your accuracy, we can do something like a 4th order accurate difference scheme for the first derivative, and here it is. And so when you put that in, along with the center difference in time that we had before, here is your new scheme. This is called Leapfrog 2-4. What we've done is we've improved the accuracy of the discretization in space to be 4th order accurate, but we're still using a 2nd order accurate scheme in time. So that's Leapfrog 2-4. Okay, a little bit more complicated scheme. I'm using more neighbors, because that's what happens when you improve accuracy to finite differences. You're usually just using more neighbors. So I've used more neighbors, but I've dropped my error from delta x squared to delta x to the 4th, which is a big improvement in spatial error. Okay, my time stepping error is still delta t squared, however, so just keep that in mind as you do this. Let's come up with a different scheme. This is called the Lax-Wendroff scheme. So this is a famous scheme, and it was partly because people really liked its stability properties, and it had some a little bit of artificial diffusion in the stepping so that it actually stabilized the scheme. So again, back to the stability properties. But what I want to do, how to develop this, is just simply say I'm going to do a Taylor expansion of u of t around t plus delta t. So if this here is just a Taylor series expansion of the solution delta t into the future. And then the question is, what do I do with these here? So you know that what you're solving is, in fact, the one-way wave equation. So you know that u of t is equal to cux. Oh, so if I have cux, then I can discretize it, and I'm going to put it right into this position here. But then I also have a second derivative in time. You can easily show if you take the derivative of this again, to get the second derivative of u in time, it's equal to c squared u xx, and I can do a center difference scheme and put that in here to end up with this Lax-Wendroff scheme here. Notice there's still the CFL number floating throughout. I have a lambda here, CFL number, and CF number squared here. And now this is the Lax-Wendroff scheme for marching the solution forward in time. So now what we have is we've got 4 schemes. We have Leapfrog 2.2, we have forward Euler in time, center difference in space. We have Leapfrog 2.4, Lax-Wendroff. We're up to 4 schemes. Let's do a 5th scheme. This is called the backward Euler scheme. So remember that before we took a forward difference in time, but remember, I always evaluate this at the current time point. But what if we evaluate this at the future time point? This may seem like a silly idea because that's exactly what we're trying to solve for. But the reason people like implicit schemes, in fact, let's work this all out. So now your stepper becomes this here, where you're solving, you're solving for the future in terms of the future. If you rearrange, here's what you get here. This tells you that here's my current point, here's my future points, and then this just becomes an AX equal to B solve. So for the future points. Okay, so this is expensive. Before I just simply computed the future points. Now I've got to solve a matrix problem in order to get the future points. But the reason people like implicit schemes is they typically have amazing stability properties. So they're harder to solve, but you buy yourself stability. So these are all the considerations and trade-offs you got to be thinking about when you come up with an appropriate scheme to solving your PDE. Keep going on schemes. So we're up to 5 schemes. Here's scheme number 6. These are called McCormick schemes or predictor-correctors. So one of the things that you like about implicit schemes is their stability properties, but it's always hard to solve for the future in terms of the future, and you have to solve this expensive AX equal to B. So what if I were to use the predictor-corrector method? It has this idea that I'll predict the future and use that prediction in my implicit scheme. So the way this goes is you first predict the future, so you use your standard scheme to predict the future, like an Euler step into the future, and now that's your prediction for this future inside of your implicit scheme. So you predict the future, and then you now make a correction to the future using the prediction of the future in this implicit scheme that you developed. So now you're no longer having to solve this AX equal to B, you're just using your prediction for of the future in the right place in order to update the solution in the future. So there's so many variants. I covered 6. There's so many more. People historically have really looked at this because what you want is the most accurate solution and the most stable algorithm possible to march forward your solution. And this depends so much upon the actual PD that you're solving. You would use very different steppers for different PD classes. So oftentimes if you're looking at a problem that's been studied for quite a while, you want to look at the literature to see what are the methods that people have developed historically that are very stable, robust, and have high accuracy properties. Because probably they figured that out, and you'd like to use the best scheme right out of the box if you can. So just a little research will often show you what people have done in that area. So stability and accuracy, those are the things that we're really considering in going after solutions, and this is what we're going to be talking about throughout this set of lectures here on time and space stepping schemes.